Welcome to the SB Grid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SB Grid.
Hello, everybody. Once again, welcome to this month's edition of the SB Grid webinar series. Just some quick procedural stuff. So next webinar is going to be on March 11th, and that's going to be Genki Terahashi from Purdue, who's going to be talking about deep main masts and DAC. And so if you have questions during today's webinar, feel free to use the Q&A feature, or you can send questions to the host through chat, and we'll moderate. And with that, so I'd like to introduce today's webinar speaker, João Rodrigues, who's a principal scientist at Schrödinger, and he's going to be talking about Phoenix OPLS-LA Glide EM. So with that, João, thank you for joining us, and again, apologies that I mispronounced your name at least once of those times. But
No, they were both good. Thank you so much. Thank you so much for the invitation and for the opportunity to present our work to the broader SB Grid community. As I was saying before everybody joined, it's a really valuable resource for everybody working in the field to have the SB Grid packages and the webinars available. So my name is João Rodrigues. I'm a principal scientist at Schrödinger, where I lead a team working on protein structure refinement. So Schrödinger, for those of you that are not aware, is a not so young company that develops computational tools for molecular design and discovery in both life sciences and material sciences. My team specifically develops software for and works closely with our structural biology team. We help them produce models of targets of interest for drug discovery programs from both X-ray data and cryo-EM data. In today's presentation, I will focus on the latter, how we have tools that help them make the most out of their cryo-EM data. So these two tools will be Glide EM and Phoenix OPLS, and I'll go through them a little bit in detail. So if you have any questions, feel free to leave them in the chat. If you have any, urgent question, feel free to say so. I'm happy to take them as we go. So, all right. For some context, for those that are mostly unfamiliar with the drug discovery process, one of the big divides in preclinical drug discovery is the existence or not of a 3D structure for the target that you are trying to develop a drug for. It's usually a protein. So having one of the structural models accelerates, of course, the program and accelerates the path towards rationalizing properties of drug candidates that you're developing. You can use these models to predict binding pockets. You can use these models to run virtual screening campaigns once you found a pocket to identify hit compounds. And you can also use these models to rationalize a whole series of properties, such as potency, absorption, distribution, toxicity, etc., for specific molecules. So I took this code from a paper that we published in Cell last year. It's a commentary on an issue devoted to structural biology. And it reads that within the realm of drug discovery, the relevance and value of the predicted structure models, this is for a paper focused on prediction, but it's also very relevant to experimentally determined structures, is directly related to their ability to rationally optimize molecular properties. What this means is that it is very valuable to have a structure, but the value of that structure only goes as far as the quality of the structure. So if you have a structure that contains errors, it's obviously not as useful as a high quality structure. So of course, the quality of the structure depends always on the quality of the data that you use to generate it. So traditionally for a long time, X-ray crystallography was the method of choice for determining atomic resolution structures. So this is just a simple statistical analysis of the PDB, and you've seen that over the last 10 years there are already over 100,000 entries, and the number almost doubled. The resolution of X-ray structures is, varied, but it tends to focus on what you consider more higher resolution structures. Sorry, which is good because the better the resolution, the more details you can see. Cryo-EM, on the other hand, emerged as a popular alternative or complementary method to X-ray crystallography in the last decade or so. So thanks to better hardware, software, and also, advantages or simpler sample preparation protocols, the number of cryo-EM structures went from, a few hundreds, 600 or so, to over 25,000 in 2025. Of course, while the resolution of these structures has been improving, it's still not as good as structures determined by X-ray crystallography, but it's getting there. And especially in the last couple of years, there's been a jump in the quality of the structures that have been determined that enabled this technique to be used more productively in drug discovery. I'm not going to go into the details of how how the sauce is made, how you go from data to a model. I'm just going to focus on a very small aspect of the whole process. For those of you that are interested in the whole process, I would recommend that you check the SPGrid channel because there are really nice talks there on those topics. But essentially, at the heart of a cryo-EM structure determination are iterative cycles of refinement and validation, where you take a map that doesn't change and you essentially try and fit atomic coordinates to that map. So as modelers do this, as people do this, they check at every cycle, how the structure looks, how it fits to the data, and how it scores in terms of some quality metrics that give you an idea of how realistic the structure is. Once someone is happy with whatever metrics they have, then that structure is usually deposited. Of course, it has to meet a few criteria. It's important to note, of course, that there is always a human component and bias in all these structures. So it's safe to say that if you put two people working on the same set of data, they will most likely arrive at slightly different structures at the end of the day. So the extent of this bias, of course, depends on the quality of the underlying data. So as we'll see in the next few slides, the resolution of the map has a big impact on how much you can model and how confidently you can model things. So here's a few examples of cryo-EM structures that are deposited in the PDB. So very few of them are very, very high resolution. And at a very, very high resolution, you can see individual atoms in the density. And here, modeling these structures is mostly unambiguous. So it's very easy to see where each atom is, and it's not very hard to place them in the right spots. So in these cases, it is quite easy to build a structure and to have a high quality structure that has very few errors. Of course, as the resolution worsens, it gets blobbier, it gets blurrier, so it becomes harder to place atoms exactly where they should be, and it becomes more a burden on the human modeler to decide and make decisions on where these atoms should be. And it's with these decisions that some errors get included in some of these structures, and then these errors will then propagate and cause issues downstream for cases like ours, where we want to use these structures in a drug discovery setting. Unfortunately, the majority of structures deposited by cryo-EM are not super high resolution. They tend to be slightly lower resolution. And specifically, when it comes to ligands, because they are smaller molecules, they are more flexible, they tend to have, generally speaking, poorer resolutions. So it is harder to model ligands into density than it is to model proteins. And there tend to be more errors associated with these small molecules in cryo-EM entries than otherwise. So here are just a few examples of structures where you can see that there is a good fit to the data. to the underlying data, but you can see that there are some atoms that are not necessarily in the density, or there are bits of density that could be explored by the molecule as well in other ways, if one were to wish so. So at Schrödinger, our team focuses on developing tools that help in this exact scenario. So we are in the business of taking initial models that you've created and, thanks to our technologies, improve them to a point where they can be directly useful in drug discovery programs. So the general pipeline that we use internally, but also that our customers use and our users use, roughly follows like this. So you get a map and you get an initial model, and use a succession of tools that we've developed until you have a model, atomic model, that can be used prospectively to test new compounds. So the three tools that I'm going to touch on today, and mostly the first two, are GlideEM and Phoenix OPLS. These two directly incorporate cryo-EM densities and mix them with our other tools to improve modeling. And then there's FEP Plus, which we use internally as the ultimate arbiter of structure quality. And it is an orthogonal method to the very more commonly used RMST calculations, for example, that allows you to verify if a structure is indeed correct or not based on a series of affinity measurements. So starting with GlideEM, GlideEM is a tool that simply enumerates ligand poses in a binding pocket. So it's a docking program, a ligand docking program. And its goal is to create poses that both make strong interactions with the receptor, that have low strain in the ligand itself, and that are consistent with whatever density that you're trying to model into. So I'm going to go a little bit over how Glide works first, and then how we've expanded it to handle densities. So Glide was published quite a while ago already, but it remains one of the best programs for protein ligand docking in the field. It is very fast, and that speed is thanks to a representation of the receptor as a grid. So there's a first step where you convert your 3D structure of your receptor into a grid. That grid is a volumetric grid, and it represents both the shape and properties of atoms in the receptor. Using that grid, we pre-generate conformations of your ligand, and these conformations go through what we call a scoring funnel. So at first, we carry out an exhaustive and systematic search of the ligand placement and conformation. So it's both a sampling of the 6 degrees of freedom of the ligand in a pocket, but also of its internal degrees of freedom in torsion angle space. And this is typically generating over 1 million or so poses for ligands. Then there's an aggressive scoring. We reduce that pool of roughly 1 million poses down to a few hundreds, and those are further refined with Monte Carlo sampling in torsional space. The goal here is that you are somewhere in the vicinity of a local minima for your structure, and you want to drill down in the energy surface to find even better structures in even better minima. Out of those few hundred structures, you pick a handful, and those are minimized and ranked based on a complex physics-based scoring function that includes terms, your usual van der Waals terms, electrostatics, lipophilicity, hydrogen bonds, strain, etc. And then you are usually left with, usually we look at the top 2 or top 1 hit, and this whole process takes a few seconds to run once the grid is generated. So there's a first cost of generating the grid that takes maybe a couple of minutes, and then running this whole sampling and scoring is incredibly efficient. So what we've done, what our team did in the past, was we've added essentially the ability of combining the grid that represents the shape and properties of the receptor with the density map. So here, essentially what we do is we tack on to the grid a representation of the map, and that will bias the search and scoring of the ligand conformations to regions of the grid that are allowed by the map or favored by the map. So the process is essentially the same. We just add at every step these map components. So the search is biased towards regions that have density. The sampling is biased towards regions that have density. And at the end, the ranking of the poses is augmented by a cross-correlation term with the density, so that when you score your poses, you will see the ones that agree, hopefully, the most with the density. Still, the rest of the glide scoring function is still there, which means that at top of getting an idea of how your ligand fits to the density, you also have an idea of how your ligand binds to the receptor and how well the conformation of the ligand also ranks. So this is a plot of a recent benchmark that we carried out of GlideEM across over 400 GPCR ligand-bound structures. And here we see the impact of the scoring function, but also of the sampling. So GlideEM, as I said, will give you at the very end 2 scores. One of them is just the fit to the density that we call dense score. There's the glide score, and we usually return 5 poses at the end of each run. So each of these runs on average took a few minutes. And that includes both the grid generation, converting the map into a grid, and then doing all the sampling. So if you look just at the raw, what's the best pose you get if you simply rank on the density score, you see that we get, for these 415 cases, a pose that's under 2 angstroms to the deposited structure over 70% of the time. Now, of course, this doesn't mean that the deposited pose is necessarily correct. It also doesn't mean that there isn't room for some alternative conformation, but it does show that the sampling and scoring we do based on density is effective at biasing the calculations towards regions where the ligand should be, or at least where a human also placed the ligand. We do find better success rates if we, instead of looking at these 5 poses that are returned, if we look at the combination of the density score with other properties that measure also binding to the receptor. And this is encapsulated in this glide score. Here you see that if you were just to take the first pose that it returned, you would get a good answer in roughly 80% of the time. What we usually recommend to people, though, is that they don't look only at the top one, but that they look at the top 5. And that is because, of course, in GlideEM, as we'll see, it's most useful in cases where there's some ambiguity in the density. And there we still want people to exercise some sort of decision making power when they are analyzing these poses. So it's I don't think any computational tool is meant to be a black box. So it is good that you have options to look for and that you're given the ingredients, in this case, the density score and the glide score, to make an informed choice yourself. And if you look at what is the best pose in the top 5 of all these runs, you see that you would find a structure that matches the deposited structure in over 85% of the time, which is very good in terms of, as far as docking success rates go. I'm just going to focus on one example. Usually people pick examples that look good. I intentionally picked an example from the other end of the scale. So I picked actually the worst case that we had in terms of results. And I think this illustrates pretty well my point before, that it is good to look at multiple poses and make an informed decision. So this is a ligand that was determined at 2.8 or 2.9, depending if you round up, angstrom resolution. And you can see that there isn't, here the density is shown at the contour recommended by the authors, and you can see that there isn't a lot of density to cover the entire molecule of the ligand. You have a few spots here and there, mostly because of those bulky rings, but generally speaking, there is pretty poor density. And one could imagine that there are multiple conformations of the ligand that fit this density as is. This is indeed what happens if you look at the poses that GlideEM returns. So here on the left of the two main images, you will have the first pose, which has an RMSD of 14 angstroms. So it's essentially a flip. The pose is just flipped upside down. And on the right, you will have pose number 3, which is in pretty good agreement with the deposited pose. What's interesting here to see is that they both have very similar cross-correlation metrics to the map. The density score, because it's a conversion of the cross-correlation to a grid, and there is some resolution loss there, does seem to hint that pose 1 is better fitting to the map. But if you look at the glide score, which is measured in kcal per mole, you see that there is over 1.4 units of difference, and that in glide terms would correspond, if you translate kcal per mole to a binding affinity, to an order of magnitude, tenfold, an order of magnitude increase in affinity. So it's a very significant change from minus 7.4 to minus 8.9. So a user looking at these 5 poses, or looking at these 2 at least, right? You would be probably picking the one on the right. That's what we would suggest. So we don't, again, think that these tools are black boxes and you should just put your map and structures in and expect it to give a perfect answer always 100% of the time. We encourage users to look at the top 5 poses and just inspect a few parameters of these scoring terms and then make an informed decision. And you see even in this case that if the best pose is completely wrong compared to the deposited pose, there's still a very good pose to be found right next to it. So in the literature, GlideEM has been cited a few times, and we've essentially seen 3 use cases for it. So this is external to Schrödinger, where we use it in our programs. So it's nice to see that the community is also using the tool, and it's using it for different purposes depending on the resolution of the map that they're working with. So we've clustered them essentially into three types of usage. So at higher resolutions, where you can more or less unambiguously model the ligand into the map, we've seen that people use GlideEM just as a validation tool. So because it's so fast, you can just run GlideEM and see if the pose that you get, or the poses that you get, are consistent with the pose that you modeled into the density. And it can also be used to provide alternative conformations for ligands. At medium resolutions, where you have some ambiguity, like that was the case above, GlideEM helps resolve these ambiguities. So it'll generate multiple poses that fit the data equally well. And you can use the rest of the scoring terms that are very accurate to discriminate between the poses. And so you can generate poses that have both good fit to the density, but also that have good internal energies, so lower strain and binding energies to the receptor. So it makes chemical sense, whatever the ligand is doing. At low resolutions, so when there is almost no density, of course, any program that relies on density will be less helpful. But GlideEM, thanks to the glide engine that underpins it, it will still be helpful in providing primitive ligand poses that have at least reasonable internal and binding energies. So glide on its own has a very high success rate for blind docking. over 85% in benchmarks. So aided by a little bit of density, it can still help generate ideas for where this pose can be. And then you can always refine the structure further or make further experiments to validate which one of these poses would be correct, as we will see at the end of the presentation. How do you use GlideEM? So SPGrid ships with a Schrodinger distribution, and you can use it either directly from our GUI Maestro or from the command line. The command line exposes more options than the GUI. So we would recommend that if you're interested in trying it out, that you might want to try with the command line first anyways. So it requires, just like Glide does, a first rough placement of the ligand in the binding site. So any Glide run will need to have an idea of what the binding site is. So here you can use either you fit the ligand to the density initially just very roughly, or if you have a homolog structure that has a ligand bound to it, then you can also use that as a starting point for the calculations. Then the workflow, it's quite simple. We have a protein preparation wizard in our suite that will handle all sorts of valence corrections, adding hydrogens, finding parameters for the ligands, for the protein, etc., optimizing hydrogen bond networks. And then once you have that structure prepared, you can just specify the ligand, import the map, and just hit run. And again, in a couple of minutes, you will have your results. And you can use it both to place a ligand where you want to do like a thorough search, or you can also use it just to adjust the placement of a pose that you already pre-positioned. So essentially do a minimization. All right, so that's it for GlideEM. So GlideEM is also coupled with a downstream tool that we use to refine further the poses. So one of the drawbacks of Glide, generally speaking, in GlideEM is that the receptor is rigid. So there's no sampling of the receptor during all these sampling and scoring of the ligand. Sometimes you do need to make small adjustments to the receptor structure as well in tandem with the ligand pose. And here is where Phoenix OPLS comes into play. So internally, our modelers in our structural biology team tend to use GlideEM followed by Phoenix OPLS, or tend to use Phoenix OPLS on its own to refine structures. So what is Phoenix OPLS? Well, it's a hybrid structure refinement protocol that simultaneously optimizes your structure against the data and against the physics-based force field. So just a little background on what happens. And again, this is a very cursory introduction to what Phoenix is. There are plenty of talks on the SPGrid channel by the Phoenix team that go in a lot more depth into what Phoenix is and what Phoenix can do. So if you're interested in that, I highly recommend checking those out. But just, general overview, both crystallography and cryo-EM structures are typically refined against an energy function. And this energy function is a combination of terms that describe the experimental data, so how well your structure fits the data, and a set of empirical restraint terms so that your structure looks like a structure at the end of the day. The restraints are derived in Phoenix mostly from high-resolution structures, and they essentially help models maintain some reasonable characteristics of stereochemistry. And this is necessary because, unless you are working with an infinitely resolved density where you know exactly where each atom is unambiguously, there's always going to be small pockets of ambiguity, and you'll have to, if you basically try and only minimize or optimize your structure against a map, you will end up with distorted bonds, distorted angles, non-planar rings, etc. So these restraints come in to try and mitigate that aspect of refinement. Of course, the problem here is these restraints are derived from high-resolution structures that are in the PDB. And while the PDB covers protein space pretty well, it does not cover ligand space pretty well. So the chemical diversity of ligands is much, much larger than the chemical diversity space is much larger than that of proteins. There are 20 amino acids. There are plenty more functional groups in ligands. So generating a statistical, essentially, potential to describe these groups is complicated from the sparse data that we have available. So as the resolution of the map you're working with, or the data that you're working with, worsens, there is less data to support modeling, and you start getting to the regime where the density doesn't play a large role, and you have to rely more on these restraints to do the work. So for proteins, there are other restraints that are usually employed when you're modeling at lower resolutions, and these are Ramachandran restraints, secondary structure restraints. For ligands, of course, these don't apply. There are no such restraints for ligands. So at low resolution or at lower resolution, as you can see here, you don't need to go that low. Without proper care and validation, ligands can be very easily overfit to the density and have high strain, for example, or just be modeled poorly. So what is Phoenix OPLS? So Phoenix OPLS essentially replaces these empirical restraints. So the terms in Phoenix that would figure out, like, how long a bond should be, what's the angle between three atoms, what's the right appropriate value for a torsion, and replaces this by OPLS4. And OPLS4 is Schrodinger's force field. It's a molecular mechanics force field, and it's been parameterized against high-level QM data, and it's validated by its ability to predict the binding affinity of ligands. So it's not validated by its, by some structural metric of RMSD or complementarity. It is validated by the ability of running simulations, and those simulations recapitulating experimental data. And this is important. So over the years, OPLS has been refined. There are multiple versions of OPLS. When Phoenix OPLS was first published, it was using OPLS 3E. So this was an improvement over OPLS 3 that had better partial charges for ligands and better description of torsions. And since then, we've released OPLS 4, which has better treatment of specific ligand groups that were rarer, and also of other properties such as hydration, for example. So including all these improved parameters in the refinement target function helps produce better ligand poses, of course, in cases where the density is sparse or ambiguous. So instead of having a lack of restraint data for these ligands, or a less accurate set of restraints for the ligands, you can rely on a very accurate state-of-the-art force field to do the work for you. So you can more confidently place these ligand molecules in ambiguous or weak density. So at the time when Phoenix OPLS was published, there weren't so many cryo-EM structures actually out there bound to ligands. So it was benchmarked on a set of 3,000 X-ray structures. And the table here on the left shows median values of certain metrics of structures that were taken from the PDB Redo database and re-refined with Phoenix OPLS. So you can see that the refinement simultaneously optimizes, again, the data, the poses against the data and the force field. And what we see is that the refined poses have essentially equivalent agreement with the data, so R3 and R-gap, but they do have fewer clashes, which is indicated by a reduced mole probability score, and also reduced ligand strain energies, meaning that the poses we generate are still as consistent with the experimental data, but they make more sense in terms of chemistry. So here are a few snapshots of those results binned by resolution. So you see that as a resolution of the data gets worse, you do start to see more of an effect of the force field as you'd expect. So at very high resolution, so that bin of like 1 angstrom, R3, for example, barely changes with the refinements, and the mole probability score is also pretty much the same. But you see that as your resolution gets worse, and particularly above 1.5 angstroms, you start seeing a marked decrease in the mole probability scores, which means that your structures are getting better, whereas the change to R3 is essentially insignificant. And you see that the ligand strain, which was one of the original goals of this whole project, is substantially reduced for over 90% of the cases. So that meant that the original pose that was deposited in the PDB had a ligand in conformations that were not favored. So it had torsions that were not at minima or angles that were stretched. And thanks to the optimization with the force field terms, this is essentially reduced or improved. Yeah, so then the improvement in mole probability score comes not only from also having fewer clashes, of course, but also from having less Ramachandran sidechain rotamer outliers. The original paper also looked at the impact of essentially how you weigh the data versus the weight of the force field in the optimization target function. So they took a few structures that were at the time available, determined by cryo-EM, and they produced these plots that have this very characteristic hockey stick shape. So in the x-axis of every single one of the 15 plots, you will have the real space correlation to the map. So the higher, the more your structure fits the map. And on the y-axis, you'll have mole probability score. So the higher you are, the worse your structure is in terms of quality. So the hockey stick pattern means that the more you increase the weight, that's what the darker colors mean, of the refinement to the data, the more you overfit your model to the data, and the more violations of angles and torsions, etc., you introduce. That's why the mole probability score is getting worse. So the white crosses are the deposited structure, and the circles are the results of refining with Phoenix OPLS with different weight combinations. So what you see is, if you look at different metrics, is that there are some signs of overfitting in these structures, meaning that you could essentially get a structure that had an equivalent or better cross correlation to the map with much improved parameters. So in this case, for example, Ramaz score. And you also see this with ligand strain, here shown as a logarithmic scale of the difference in energy between the starting and the finishing pose. And you see that the majority of structures actually had quite some strain. So this also highlights the interplay between the data and the force field. So it's not that this is, again, a black box that you just run with one set of parameters. We do offer a tool, much like the one in Phoenix, that does a weight scan and helps you select what are the best combination of weights for your particular structure. And if you go by the weights that are suggested by this tool, you are more or less guaranteed to have a sweet spot of a good correlation to your map, but also maintaining decent stereochemical qualities of your structure. So this was the sort of short or not so short overview of GlideEM and Phoenix OPLS. And I'm not going to go much in depth about FEP+, but this is roughly the workflow that people at Schrödinger use. So I'm going to highlight just two use cases that were published by our teams. So the first was a paper published in PNAS in 2021. So our team was working on CTP syntase 1 which is an important immune response factor. And they were aiming for a selective inhibition of CTPS1, so one isoform of the enzyme, but not of CTPS2. And this was because they wanted to, when you design drugs, you usually want them to be specific. You don't want them to just go and like hit a bunch of different proteins at the same time. And here, this was made even more complicated because they're not completely different proteins, but just two different isoforms. So the team set out to build or to get structures of the two isoforms, and they essentially used a combination of GlyDM and Phoenix OPLS to build structures of these enzymes, complex to the ligands, starting from homology models. So and these structures then allow them to rationalize a single amino acid change that was responsible essentially for binding to the ligand and distinguishing between the two isoforms. So this is a simple but very powerful example of how you can use these tools to arrive at atomic insights, essentially, that explain the function or the binding of a target. And the second example, just to show how FEP can be used sometimes in this context. So the team earlier, in collaboration with Nimbus and researchers at Columbia, if I'm not mistaken, was working on an ATP citrate lyase. So this enzyme, when inhibited, leads to the reduction of cholesterol and fatty acid synthesis, essentially. There was a crystal structure of the enzyme, but it only had density for an N-terminal segment, so a specific domain. And this was insufficient to explain how a series of molecules, congeneric molecules, similar molecules, were binding and inhibiting the enzyme. So the team got a cryo-EM structure of the entire enzyme, and it showed that there was significant loop motion in this binding site that opened a new allosteric pocket. The density wasn't great. It was, I thought I had it on the slide. It was like 3 point something, quite low. So the team also used an orthogonal method to validate that their pose was correct. So this predates GlyDM and Phoenix OPLS. So that method was FEP. And FEP essentially is a method, a simulation-based method, that allows you to predict binding affinity data. And it has a predictive accuracy that approaches that of experiments, so within 1 kcal per mole of error. And it's been validated across several large-scale benchmarks that target both different ligands, but also different protein classes. It is important because it is an orthogonal method to a lot of what we do in structural biology. So it takes essentially a series of measurements of binding affinity or inhibition, and then it then tries to correlate, to predict these values, and then gives you a correlation at the end. So what the team did in this case was they launched these FEP calculations using a known series of inhibitors that were congeneric, using the cryo-EM pose as a starting point. And these calculations showed that there was a significant correlation between what they predicted and what they had observed in their measurements. So this meant that the ligand placement was correct. So FEP is extremely sensitive to wrong placements of ligands. So if the ligand had been incorrectly placed, if it was flipped, etc., then likely there wouldn't have been a signal. So yeah, so with that, I guess open the floor to questions. I'd just like to leave some acknowledgements. So the structure refinement team at Schrödinger right now is composed of Jake, Hande, and Gabi, 3 fantastic scientists. A lot of the work done here was spearheaded and carried out by former team members and collaborators, namely Hido Ken, Mike, and Yorgos, and also the Phoenix team for the work with OPLS. So yeah, and with that, I'd like to thank you. Thanks again, SB Grid, for the invitation, for the opportunity. And here are some references if you want to follow. And also our education team has also offered a coupon for those of you in the audience that want to explore our online courses. You can use it to get a discounted rate. So, and with that, I'll open the floor to questions if there are any.
Great. Thank you. That was really cool talk. And again, so if folks have questions, you can use the Q&A, you can use the raise hand gesture, you can send them through chat. And I have a couple of questions where we can wait for some of these to come in. And advanced warning, not all of my questions are fully coherent. So if the question doesn't make sense, call me out on that. But
no worries.
So for the GlideEM portion, how does it work with the orthogonalization of the map grid versus the glide density grid, or the glide docking grid? Like, do those have to line up necessarily?
Yeah, sorry. So the structure needs to be pre-aligned on a map. Yeah. So
okay.
if I interpret your question correctly, yeah, the structure needs to be pre-aligned on the map. So usually from what we've seen, people model in the receptor, they have a good idea of where the receptor roughly is, and then you still have some empty density that you want to place the ligand on or refine it, and that's where GlideEM comes in. Yeah.
I guess I'm just thinking of the case where I've had a ligand pocket where the structure has that ligand pocket in a way that doesn't necessarily fit with the Cartesian grid for glide docking. So I've had to like rotate things around. It sounds like if you do something like that, you would have to do that. You'd have to do the same thing with your density that you're trying to run.
Yes. Through. Yes. Yeah.
Cool. And I'm pretty sure that you mentioned this, but just to double check, GlideEM does that do any attempts to balance the weighting factor between the density and the glide score, or is that just eyeball it and see?
That's eyeball it and see. So there are parameters that you can set to both control the weight of the density at the different stages of glide, but when GlideEM was first published, there weren't enough cases to actually warrant this kind of, large scale benchmarking. And that's what we've done recently, thanks to the few, thousands of structures that were published since. So we're exactly looking into that as well. But from what we've seen, it seems to be doing a pretty decent job at fishing out poses that are roughly placed within the density, but still make sense chemically. But those are parameters you can tinker with if you want. And again, because these searches are so quick that doing even like a scan would be trivial in that sense.
Yeah. Is this something where people have used it for trying to identify which ligand is in their density? Or?
That's a very good question. I've never heard of that kind of application. I didn't talk to someone last year that thought exactly of doing that. So one way you could try and do this was to do some sort of virtual screening into the density. So where you have a library of possible compounds. So this was someone who was working on pro-EM structures from cell extracts. So who knows what's in there? And this was the suggestion was you can take a library of what you think is in your extract and then try and like dock it to see which one gives you the best score and best fit. So Glide has been designed from the get-go for virtual screening, which is a very similar task, right? You have like a library of compounds and you want to see which ones bind more effectively. So I don't see that there would be any barriers to that application.
Yeah, I mean, it does seem like it would be a great tool to try out for that, and it's definitely popped into my head for the crystallographic issue and the cryo-EM issue of I have this density, I'm not sure what ligand is in here.
Yeah.
And we have it hooked up to a tool that's designed for looking at lots of ligands. So
Yeah. No, it's true. Yeah. It's a very good suggestion.
yeah. All right. I think we have a two-parter. So is there a maximum size for the ligand, and would it work for like binding peptides?
Yes, sorry, I completely ignored peptides because because this benchmark that we've run recently focuses only on small molecules. But yes, there is a peptide mode. So there is a maximum limit for what Glide can handle. To be fair, that limit is much higher than what how can I put this? That limit is much higher than what you'd expect Glide could handle reasonably, right? Because if you give it a molecule that has so many rotatable bonds, if you give an entire protein, right, then you'll be out of luck with any sampling method that is as exhaustive as this one. So yeah, but for peptides, there is a specific mode to sample peptides. So Glide has also been used for peptide docking. There's a separate publication for that, and GlideEM also leverages that, and it can dock. It's been used to, for example, dock peptides into the mu opioid receptor and discriminate between poses. And I don't have the slides here, but if you go to the original publication, you'll find the images. So the different poses were showing, for example, a different crankshaft motion in the backbone of the peptide. And the scores were discriminating between. So they both equally fit to the density. The scores were roughly the same as well. And then through comparison with other deposited structures of the mu opioid receptor, the team was able to figure out which one would be the correct one. So yeah, so it works for peptides, long story short. Yeah.
Cool. Yeah, the only size limit I've personally run into with Glide has been if I'm not double checking myself and my search box is too small to actually fit the ligand in. Then that does,
Yeah.
you know.
Yeah. So Glide, as I mentioned, needs the notion of a binding site to define a search box. That's how it works. And there are the two ends of the scale, right? There's a too small of a box. So what you could do is, usually that is derived from the ligand you're trying to dock into. So it might happen that if you have a very flexible ligand and you just happen to give it a very collapsed conformation, that you might then hit, like, in the extreme, very open conformation doesn't fit the box that it created. But we've also seen, and we don't recommend this, that people use the entire protein as a grid because this reduces a lot, of course, the sampling power, and it's just like not what this was designed for. So you do need to have an idea of where the pocket is before using this tool optimally, of course. I mean, you can use it in any way, but
Yeah.
you get best results if you use it this way.
And I've forgotten the name, but Schrodinger does have a tool for, if you're not sure where the binding pocket is, it will say, these are plausible binding pockets. Why don't you take a look here?
Exactly. So there are two tools you can use. One is called sitemap, which is exactly that. So you'll analyze your receptor and you'll find like cavities that are pocket-like. Based on some properties, but we also have a tool that uses molecular dynamic simulations with mixed solvents. And that one is more useful for opening pockets that would otherwise not be readily accessible. So this it's a method that takes advantage of different simulations run with different probes in the solvent box, and then those probes will diffuse and then find pockets in the protein, and then there's an analysis of all these simulations together, and then you will see what possible pockets you might have open. And that is quite powerful because you can also then use those probes as a hint for what kind of groups would bind to what kind of pockets. So if you have a very hydrophobic probe and it always binds to the same place, you'd expect it to bind like a very hydrophobic moiety of a ligand, something like this. So yeah, so we have different tools to do that. Yeah.
Great. Cool. Nice. One other question is there anything restricting using the density from GlideEM to, can that be other types of density like X-ray crystallography density or microelectron diffraction density?
Yeah, so the talk was very specifically focused on GlideEM and Phoenix OPLS, but we have been working. So Hande from the team has been working on Glide Extel, which is essentially what that is. So it's an application. It's essentially GlideEM geared towards X-ray data. And the manuscript is being written, so we could expect that work to come out soon. But yeah, but so far we've seen pretty good performance as well. Yeah, across like also a variety of targets and resolutions. So yeah, and the tool works essentially in the same way.
Cool. All right. I guess one last call for questions, and okay, looks like no. So once again, thank you very much for joining us, and that was a very cool talk. And that's you're adding to my list of papers that I want to read. So.
All right, good. That's what one can wish for. Thank you so much for the invitation again, and thank you everyone for staying.